Okay.
Doctor, could you please share your screen?
Yes. Can you see the our presentation?
Yes, yes. Could you please make it into presentation mode?
Can I?
No. Could you please maximize your screen, your PPT?
Yeah. I had some problems with in the screen.
No. The last one was PPT. Yes. Could you please maximize your document? Doctor, could you please double click on the document?
Okay.
No. Actually, you're minimizing. Could you please double click on the document?
I minimize the document. Yes.
No. You need to maximize.
Okay. Yes. It's okay.
Yes.
Can I just start?
Yes.
Okay. The sound is okay? Okay. Okay. Good afternoon. I thank all of you for your attention to this investigation. This work is related to the pyrolysis of expanded polystyrene as a possible solution to create a sustainable process where styrene could be recycled. The content of our presentation, next, please, the next slide. Next. Okay. The content of our presentation includes 7 aspects as shown. The environmental problem with expanded polystyrene or WIPs is that it's abundant and floats in the oceans and also in landfills. Like most synthetic polymers, WIPs degrades very slowly by the UV radiation effect from the sun, producing smaller particles which can be easily ingested by marine fauna. In Mexico City, around 191 tons of WIPs were produced every day in 2020. Some authors, such as Shakura, have mentioned some potential uses as WIPs. First, it can be reprocessed by recycle making composites. Second, it can also be reused to obtain polymer clays nanocomposites. Third, a high value added products such as adhesives, paints, super absorbents, polystyrene nanofibers, flocculants, and ion exchange resins. For the conversion to styrene monomer through a pyrolysis process, the present work proposes this last method to take advantage of WIPs by producing its styrene monomer through a pyrolysis process. Well, the literature review of WIPs pyrolysis can be divided into studies with different types of reactors and catalysts with certain activity and selectivity. A large number of simple flux type reactors made of glass or stainless steel are observed. Then semi-continuous reactors, then autothermal fixed bed reactor, and finally the conical spotted bed reactor. Regarding the catalyst, we have found metal oxide supported metal catalyst, hydrotalcites, and zeolites. It has been found that when using acid solids as catalysts, high amounts of benzene, non-condensable gases, and polycyclic aromatic hydrocarbons are obtained. On the contrary, using basic solid as catalyst results in higher styrene yield and fewer non-condensable gases. The main objective that needs to be achieved in this study is to convert WIPs into styrene with a basic magnesium oxide catalyst using a rotary reactor. The WIPs collection consisted of waste plates and disposable cups, electronic material packaging, and other type of packagings. In the case of crushing and grinding of WIPs, we use a mill with fixed moving blades to obtain WIPs with sizes of less than 2 centimeters, as can be seen in the photograph. A semi-batch glass reactor was built to carry out the first low temperature pyrolysis reactions. Experiments were done with catalyst named G1 and without catalyst named GO. The reaction conditions in the installation are shown. The WIPs was dissolved in toluene, and nitrogen was used as a carrier gas. The maximum temperature was 250 Celsius. The ratio of WIPs to catalyst was then to 1 by weight. Magnesium oxide was used as powder catalyst, US mesh 100. The reaction vapors were condensed into condensers cooled with a methanol water mixture and dry ice to -5 degrees Celsius. The oily liquid could be removed at specific times and analyzed chromatographically. Following the pyrolysis reaction of WIPs in toluene, the beginning of the formation of white vapors is observed at 140 Celsius, while the production of condensate is observed at 250 Celsius. For a longer time, at 300 Celsius, the presence of white vapors continues in the reactor until when the presence of these vapors ends. A black carbon liquid solid is found at the bottom of the reactor. The analysis procedure for the samples in liquid and gas phase was chromatography. Shown here are the columns, chromatographs, and operating conditions of the variant chromatograph. Chromatograph of the main products in the liquid phase is also shown, which were toluene, ethyl benzene, and styrene. The recommendations of the ASTM method were followed for this purpose. In this diagram of the installation of the rotary reactor, we can see that it is composed of the tubular reactor supported by eight bearings for its rotation. The exit gases from the reactor are sent to a stainless steel condenser using a mechanical seal and a thermal expansion joint to prevent gas leaks. At the outlet of the condenser, there is a separator tank for the gas liquid phase. The gas phase is sent to one of the two burners to heat the reactor. The liquid phase is extracted through a valve for analysis. The condenser used water at room temperature. LPG gas was used to heat the reactor, which was measured by a suitable flow meter. The temperature was measured at the axial center of the reactor using a fixed thermocouple. Various materials were used for insulation: metal mesh, fiberglass, cement for refractory use, and ceramic fiber. In this photograph of the installation, you can see the reactor connected to a mechanical seal, a thermal expansion joint, and the condenser. Two gas flow meters are shown on the front. In the lower rear part, you can see the water tank of the cooling circuit. In the photograph below, you can see the 8 centimeters thick thermal insulation system. Here you can see the expansion joint to prevent leaks and the burners too. 4 experiments with fresh catalyst and 4 experiments with regenerated catalyst are shown in the table. The experiments with normal heating are shown in purple, with an average temperature of 454 Celsius, and experiments with enhanced heating in blue, at an average temperature of 508 centigrades. The profile of temperatures against time with load and without a load of whips is also shown. 460 grams of whips were used with a ratio of 10:1 of whips to catalyst. Neither solvent nor carrier gas was used to make this process most cost-effective and sustainable. Results. The production of liquid phase in this reactor, I am talking about the glass reactor, was proportional to the rise in the temperature, as also observed in the temperature versus time profile. The liquid production at 260 Celsius was 78%. The gas production was 9.7%, and the solid was 11.7%. The products obtained were toluene, ethyl benzene, styrene, and heavier products. The gases were butene and butylene in small proportions. It was found that the presence of catalyst improved the styrene gel compared to the experiment without catalyst as a function of reaction time and temperature. A temperature of 250 Celsius, styrene gel of 56% was found, named G1, while a gel of 23% was found for the experiment without catalyst, named GO. Authors such as Zhang reported a styrene gel of 56% without a catalyst and slightly higher styrene gel of 63% with an magnesium oxide catalyst at 350 degrees Celsius. At the beginning of in this case, these results here related to the rotary reactor. At the beginning of the pyrolysis in the rotary reactor, a large volume of liquid products with a very high styrene concentration was obtained. As the reaction progressed, a decrease in the concentration of styrene was observed, and the concentration of toluene, ethyl benzene, and heavier products increased, but a considerable reduction in the volume of liquid products was observed. In all the experiments, the same weight loss as a function of time and the weight evolution over time of the liquid fraction trend was observed, even when the regenerated magnesium oxide catalyst or no catalyst was used. A greater gas gel compared to liquid gel was observed when no catalyst was used. Liquid gel increases with temperature with or without catalyst. The gas gel decreased with an increase in temperature with catalyst. All experiments with a regenerated catalyst showed almost the same performance towards liquid product. The liquid products, the liquid product yields show that this strain is the main product, as you can see. Catalytic degradation with solid bases could begin with the formation of carbocations by removal of hydrogen atoms from polystyrene absorbed on basic sites according to the reaction mechanism model proposed by Chang. Thermal pyrolysis without a catalyst could originate with a random formation of polymeric radicals. Here in the experiments with fresh magnesium oxide catalyst with normal insulation, the catalyst favored the presence of toluene, similar to the experiments with regenerated catalyst and improved insulation. Toluene production, on the other hand, was lower in the experiments without catalyst. In comparison with other studies on the pyrolysis waves, we observed that the majority of the 4 studies with strain yields greater than 71% used catalyst. Also, the reaction temperatures varied from 350 Celsius with Chang to 528 Celsius with Perez. As might be expected, strain performance is more favorable at high temperatures. The studies by Chang at 350 Celsius and Imani at 410 Celsius could be interesting with yields of 70% and 78% respectively, due to the low temperatures they used. The characterization by nitrogen fission of the unevaluated magnesium oxide catalyst showed a small area of 45 square meters by gram. By X-ray diffraction, the structure called periclase was identified. This structure didn't change after the reaction. Reflections due to carbon deposited in the evaluated catalyst were also observed. In this slide, you can see the observation by scanning electron microscopy of the untested, no evaluated, magnesium oxide catalyst shows the following elements: magnesium, oxygen, silicon, and calcium. This is a map. Electronic map. The observation by scanning electron microscopy of the tested magnesium oxide catalyst shows the following elements: carbon, silicon, sulfur, magnesium, oxygen, and calcium. The analysis of the carbon deposited in some catalysts was carried out by thermal gravimetric analysis, obtaining carbon concentration of 9 to 13 weight%. Well, these are the conclusions. The best strain yield was directly related to a higher temperature. The effect on magnesium oxide catalyst was more significant at low temperatures than at higher temperatures. In a rotating steel reactor at high temperature, a high yield of styrene was obtained from waves by thermal catalytic pyrolysis, and the magnesium oxide catalyst maintained its catalytic activity after 4 regenerations. It was found that the movement in the rotating reactor also helped to obtain a higher styrene yield than when the reactor was static, because the reactant bed back mixing took place, and heat transfer was improved, and this the heat transfer was improved, and magnesium oxide catalyst was mesoporous and didn't undergo any modification after pyrolysis. So it can be reused with good results, employing its regeneration at 600 degrees Celsius before reuse. The carbon deposited on the catalyst was easily removed by calcination. This is the acknowledgements to the National Council of Humanities, Science and Technology from Mexico government, to the Metropolitan Autonomous University, to the National Polytechnic Institute, to the Mexican Petroleum Institute, and the company Síntesis and Aplicaciones Industriales of Mexico. Thank you for your attention. Thank you for your attention.
Thank you, Doctor, for your presentation. Any queries from the group? Okay, that will follow up on our next presentation. I would like to call Meera to as the speaker is not available right now, so she has shared a pre-recorded video. We would like to play the record. Please go to the video and please make note of all your queries so that we can share the queries to the professor. Doctor, could you please stop sharing the screen?
Okay.
Thank you, Doctor.
Thank you. Okay, let me. Okay.